Why does anything exist at all? This is not just a philosophical question. It is a concrete scientific problem. Our universe, with its galaxies, stars, and planets, appears to be a statistical impossibility. According to the fundamental laws of physics, everything we see should not be here. The cosmos seems perfectly fine-tuned for existence in a way that defies all odds. In this exploration, you will uncover the shocking reasons why our reality is a cosmic anomaly. We will investigate why the universe should have collapsed instantly or flown apart into nothingness. And we will confront the eerie precision of nature's constants that makes your very presence a near miracle. What does it truly mean that we are here against all probability? The most logical state of reality should be absolute nothingness. No space, no time, no matter, not even the empty void we sometimes picture. Pure, undiluted non-existence. Yet here we are in a universe brimming with galaxies, stars, and planets. This is the foundational mystery, the problem of something versus nothing. Why is there a cosmos at all? Think of a light switch in a vast, dark, and eternal room. The default position is off. For the light to be on, someone or something must have flipped that switch. Our universe is that light, inexplicably burning in an endless night. For existence to even begin, a series of incredibly specific conditions had to be met. It is as if a lock with a near infinite number of combinations opened on the very first try. These conditions are not just about having the right ingredients like matter and energy. They are governed by a set of cosmic rules, numbers so precise that the slightest deviation would have rendered the universe stillborn. What are these mysterious numbers, and why do they seem perfectly tuned for our existence? These numbers are the universe's deepest operating rules, written into the fabric of reality itself. Think of them as the cosmic dials that were set at the moment of creation. The force of gravity, the speed of light, the strength that holds atoms together, each is defined by a specific, unchanging number. The shocking truth is that these values are not random. They are fine-tuned with a precision that defies belief. If any one of these dials were turned even a hair's breadth in either direction, our universe would be utterly unrecognizable and life would be an impossibility. Take gravity, for example. The gravitational constant determines how strongly matter pulls on other matter. If this force were just slightly stronger, the universe would have collapsed back on itself in a catastrophic crunch moments after the Big Bang. There would be no time for stars to form, let alone planets. But if gravity were even a tiny bit weaker, matter would have flown apart so rapidly that it could never clump together. Galaxies, stars, and solar systems would never have coalesced. We would have a cold, dark, and empty cosmos. Then there is the strength of the force that binds atomic nuclei. This force must be exquisitely balanced. If it were a little stronger, all the hydrogen in the early universe would have fused into helium, leaving no fuel for the stars that power life. Water, a cornerstone of life as we know it, would not exist. If this nuclear force were slightly weaker, heavy elements like carbon and oxygen, the very building blocks of our bodies, could never form inside stars. The universe would be a sea of simple, boring hydrogen, incapable of creating anything complex. Even the expansion rate of the universe itself had to be perfect. Picture a pencil balanced perfectly on its tip. If the initial push of the Big Bang had been a fraction too weak, gravity would have won, pulling everything back into a black hole. If the expansion had been a fraction too strong, the cosmic fabric would have stretched so thin that matter would be scattered into a meaningless mist. Our universe hit that pencil-perfect balance, allowing for just the right amount of structure to form over billions of years. This level of precision is staggering. It is like a lottery where the odds of winning are 1 in many trillions, and yet we are holding the winning ticket. The constants of nature are set to such exact values that their alignment for a life-permitting cosmos seems like a miracle. This cosmic fine-tuning forces us to ask a profound question. Are we just the beneficiaries of an inconceivable cosmic accident, or is there a deeper reason why the numbers are just right? This staggering fine-tuning reaches its peak with one of the most baffling numbers in all of physics, the cosmological constant. This is the energy density of empty space itself, a faint pressure that pushes the universe apart. According to our best theories of the quantum world, the vacuum of space is not truly empty. It is a seething, bubbling foam where virtual particles flicker in and out of existence in a constant dance. All this frantic quantum activity should fill space with a colossal amount of energy. When physicists calculate this predicted vacuum energy, the result is a number so immense it defies human comprehension. It should be a 1 followed by 120 zeros. This is the energy the universe should have, but when astronomers measure the actual energy of empty space, the value they find is almost zero. It is a tiny, gentle nudge, not a cataclysmic blast. The difference between the prediction and reality is not a small error. It is a miscalculation of 120 orders of magnitude. To grasp that scale, imagine every single grain of sand on every beach and in every desert on Earth. Now, imagine you are searching for one specific marked grain. The gap between theory and observation is vastly larger than the odds of you finding that single grain by pure chance. This is not a minor oversight, it is a crisis for fundamental physics. The consequences of this miscalculation are absolute. If the vacuum energy were anywhere near the colossal value predicted by quantum theory, the universe as we know it would be impossible. That immense repulsive force would have torn the fabric of spacetime apart in the first fleeting instants after the Big Bang. Every single proton, neutron, and electron would have been blasted away from every other, flying into an eternal, lonely darkness. Not a single atom could have formed, let alone stars, planets, or people. The cosmos would be a meaningless, thin, and ever-expanding void. The fact that we are here to ponder this means the cosmological constant is not just a little fine-tuned. It is fine-tuned to an almost impossible precision, set to a value so close to zero that it allows for our complex reality to slowly unfold over billions of years. How can this be? How can our most successful theories be so spectacularly wrong about the energy of nothing? This enormous discrepancy, known as the cosmological constant problem, stands as perhaps the greatest unsolved mystery in theoretical physics. It suggests we are missing something profound, a deep principle of nature that miraculously cancels out almost all of this vacuum energy, leaving behind just the faintest whisper that we can detect in the accelerating expansion of the universe. This is not just a number on a page, it is the razor's edge upon which all of existence balances. This razor's edge of fine-tuning is not the only cosmic lottery we have won. There is another, equally baffling imbalance written into the first moments of time, one that determined whether anything would be left behind to build a universe at all. According to our most fundamental laws of physics, the Big Bang should have been perfectly symmetrical. It should have created equal amounts of matter and antimatter. For every particle of matter born, a mirror image particle of antimatter should have sprung into existence. These two are perfect opposites, destined to destroy each other in a flash of pure energy upon contact. This process is called annihilation. If the universe had followed this elegant, balanced script, all the matter and all the antimatter created in the initial fireball would have met, annihilated, and left behind a cosmos containing nothing but light. There would be no residue, no stuff, no building blocks for anything. The universe would be a vast, expanding sea of radiation, forever empty and dark in the sense that there would be nothing to see, nothing to touch, nothing to form into galaxies or life. Yet here we are, our bodies, our planet, and every star we see in the night sky is made of matter. This presents a profound mystery. Where did all the antimatter go? For our universe to exist, for even a single atom to survive that primordial conflict, a fundamental rule had to be broken. Somehow, for every billion pairs of matter and antimatter that annihilated each other in the early universe, one single particle of matter was left behind. 1 in a billion. Think of a colossal cosmic war where two perfectly matched armies completely obliterate each other. Yet when the smoke clears, a single soldier from one side remains standing. That solitary survivor is the reason we are here. Every galaxy, every star, every planet, and every one of us is made from the leftovers of that ancient battle, the tiny excess of matter that did not get annihilated. Physicists call this the matter-antimatter asymmetry, and it remains one of the greatest unsolved problems in science. We know this imbalance had to occur, but we do not know the mechanism that caused it. What process in the infant universe favored matter over antimatter, even by this incredibly tiny margin? The search for this cosmic bias is relentless. Scientists recreate the conditions of the early universe in massive particle colliders, smashing particles together at nearly the speed of light, hoping to catch a glimpse of a law of physics that treats matter and antimatter slightly differently. They study exotic particles with extreme precision, looking for any tiny crack in the perfect symmetry. So far, the mystery only deepens. The known differences are not nearly enough to account for the overwhelming dominance of matter we see in our cosmos. This means our understanding of physics is incomplete. There is a fundamental process, a new law or a new particle that we have not yet discovered, a hidden actor that tipped the scales in our favor in the first fleeting second of everything. Without that 1 in a billion advantage, reality would be a featureless void. The fact that we are here to question it means we are living proof of a broken symmetry, the beneficiaries of a cosmic imperfection that made all the difference. This cosmic favoritism for matter is not the only impossible balance we must account for. The very shape of our universe, its large-scale geometry, is another monument to fine-tuning. The cosmos is, for all intents and purposes, perfectly flat. This is not flat like a tabletop, but flat in the sense of its spatial geometry. In a flat universe, parallel lines will never meet, and the angles of a triangle always add up to exactly 180 degrees. This might sound like a simple, even expected outcome, but it is actually a state of incredible and unlikely precision. The problem is that the universe could have easily been born with a different shape. It could have had positive curvature like the surface of a sphere, causing it to eventually collapse in a big crunch. Or it could have had negative curvature like a saddle, leading to a runaway expansion that would tear everything apart. For our universe to be flat, its initial density had to be exactly critical. The amount of matter and energy in the cosmos had to perfectly balance the expansion rate from the Big Bang. This balance is measured by a number called the density parameter, and for a flat universe, this number must be exactly 1. Not 0.999, not 1.001, but precisely 1. The mystery deepens when we wind the clock back to the very beginning, to an almost incomprehensibly brief moment after creation known as the Planck time. At that instant, the universe was smaller than an atom, and the density parameter had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. To understand a number that vast, try to visualize every single atom that makes up our entire planet Earth. Now multiply that number by 1 billion. The precision required for the universe's flatness is far greater than the challenge of picking one predetermined atom out of that colossal pile. A deviation by just 1 part in that astronomical number would have been catastrophic. If the density had been even a minuscule fraction higher, the extra gravity would have quickly overwhelmed the expansion, pulling the entire universe back into a singularity long before stars could ever form. If the density had been a minuscule fraction lower, the universe would have expanded so rapidly that no galaxies, no stars, and no planets could have ever coalesced from the thinning cosmic soup. we would be left with a cold, empty, and utterly dark void. The fact that we live in a stable, structured cosmos that has lasted for billions of years means this dial was set with near infinite care. This is the flatness problem, and it screams that the initial conditions of our universe were not random. They were orchestrated with a precision that dwarfs human understanding, setting the stage for everything that was to come. This impossible flatness is intimately connected to another, even more baffling cosmic riddle. Look up at the night sky in any direction you choose. Now turn and look in the exact opposite direction. The universe you see in both views is remarkably, almost eerily, the same. The temperature of deep space, the distribution of galaxies, the very texture of the cosmos is uniform to a degree that defies all logic. This is the horizon problem, and it challenges our most basic understanding of space and time. The issue stems from the speed limit of the universe, the speed of light. Since the Big Bang, light has had a finite amount of time to travel. We can calculate a cosmic horizon, the maximum distance any signal, including heat, could have possibly reached since the beginning. Now consider 2 points in the sky that are separated by a vast distance, points on opposite horizons. According to the standard story of the Big Bang, these 2 regions have never been in contact. Their past light cones do not overlap. They are like 2 isolated islands that have never shared any information, not even a single photon. There has simply not been enough time since the universe began for light or any form of energy to travel between them and allow their temperatures to equalize. Yet, when we examine the cosmic microwave background, the ancient afterglow of the Big Bang, we see something astounding. That faint radiation bathing the universe is uniform to better than 1 part in 10,000. It has the same temperature everywhere in every direction with only incredibly tiny fluctuations. How can this be? How can 2 regions that have never communicated, never exchanged a single bit of energy, somehow agree to be at the exact same temperature? It is as if you placed 2 cups of coffee at opposite ends of a gigantic cold stadium. Without any connection between them, you return an hour later to find both are still precisely 90 degrees Celsius. This is not just unlikely, it is physically impossible under the known rules. The hot coffee should have cooled at different rates, influenced by tiny, random drafts. The universe should show vastly different temperatures in different directions, a patchwork of hot and cold spots reflecting its chaotic infancy. Instead, we see a profound and smooth sameness. This uniformity is a powerful clue that our standard picture of the Big Bang is incomplete. It suggests that these distant regions of the universe were, in fact, in close contact at some very early point. They must have been causally connected, able to share energy and reach a common temperature before being driven apart. But how could that happen if the universe was not old enough for light to have made the trip? The most compelling solution proposed by cosmologists is a dramatic event called cosmic inflation. This theory posits that in the first fleeting fraction of a second, the universe underwent a period of hyper-accelerated expansion. Space itself stretched faster than the speed of light, magnifying a tiny, interconnected patch of the primordial cosmos into the vast observable universe we see today. In this scenario, the entire sky was once a single, tiny, unified region where everything was in thermal equilibrium. Then, inflation blew it up to cosmic size, preserving that original uniformity across distances that now seem impossibly separate. The horizon problem forces us to confront a universe that seems more coordinated, more unified than it has any right to be. It points toward a hidden chapter in the very first moments of time, an event of such immense power that it set the stage for the structured and coherent cosmos we inhabit today. Without this mysterious synchronization, our universe would be a jagged, chaotic mess, not the smooth canvas upon which galaxies could eventually form. This profound synchronization in the early cosmos points toward an origin even more bizarre than we have yet considered. To find it, we must venture into the strange realm of the very small, where the very concepts of something and nothing lose all meaning. At the heart of quantum mechanics lies a principle that utterly upends our everyday experience, the uncertainty principle. This rule states that on the tiniest scales, the universe is inherently fuzzy. You cannot precisely know both the energy of a system and the exact time you are measuring it. This is not a limitation of our instruments, it is a fundamental property of reality. One astonishing consequence of this quantum fuzziness is that empty space is not empty at all. The void is a seething, turbulent sea of activity. Particles and their antimatter counterparts spontaneously blink into existence, borrowing energy from the vacuum for an unimaginably brief moment before colliding and vanishing back into nothingness. These are virtual particles, and they are not just a mathematical trick. We can measure their effects. This constant, frantic creation and annihilation is happening everywhere all the time, in every single cubic centimeter of what we perceive as nothing. This phenomenon, known as quantum fluctuation, challenges our deepest intuitions. True nothingness, it seems, is unstable. The universe appears to have a fundamental restlessness, an irrepressible tendency to become something. This leads to a breathtaking possibility. What if our entire universe is the ultimate quantum fluctuation? A fluctuation so vast and so enduring that it spawned everything we see. In this radical view, the cosmos could have simply popped into existence from nothing, a monumental bubble of space-time that defied the odds and did not immediately pop back out of existence. The energy for this cosmic birth would have been borrowed, with the positive energy of all the stars, planets, and galaxies perfectly balanced by the negative gravitational energy of the cosmos itself. In a sense, the total energy of the universe could be zero, meaning it required no net energy to create. We could be living in the aftermath of the most ambitious loan in existence, a loan from nothing that never has to be repaid. This idea forces us to redefine nothingness itself. It is not a serene, static void. It is a cauldron of potential, a realm where the laws of physics allow for spontaneous genesis. The question then shifts from why there is something rather than nothing, to why this particular fluctuation resulted in a stable, long-lived universe with such incredibly fine-tuned constants. The quantum vacuum may be fertile, but it mostly produces short-lived chaos. Our orderly cosmos is the profound exception, not the rule. We are left wondering if our universe is just one bubble in an infinite, frothing multiverse, a single lucky roll of the quantum dice in a game without end. This quantum instability leads to a thought experiment so strange it seems to question the very reality we perceive. The idea is known as the Boltzmann brain paradox, named for the physicist Ludwig Boltzmann, who first wrestled with the statistical nature of order. The paradox begins with a simple, undeniable fact. Our universe is a place of incredible order. From the precise laws of physics to the complex structure of our own minds, everything we see represents a state that is vastly improbable compared to the chaos that should dominate. In any closed system, disorder or entropy always increases. A shattered cup does not reassemble itself. Smoke does not flow back into a cigarette. The natural trend is toward randomness. So how do we explain our highly ordered existence, not just for a moment, but sustained over billions of years? One potential answer lies in the concept of statistical fluctuations. Even in a state of maximum chaos, random jitters can momentarily create pockets of order. In an infinitely old or infinitely large universe, every possible arrangement of particles, no matter how unlikely, should eventually occur by pure chance. This is where the paradox becomes deeply unsettling. If we are just a random fluctuation in an eternal sea of chaos, what is the most probable form that a conscious observer would take? Would it be an entire, ordered universe with a long history of galaxies and planets, leading slowly to the evolution of billions of conscious beings like us? Or would it be just a single, self-aware brain that spontaneously forms complete with false memories, floating for a fleeting instant in the void? The mathematics is terrifying. The energy required to conjure a single, disembodied brain from random particle collisions is astronomically smaller than the energy needed to create an entire cosmos. The probability of a Boltzmann brain popping into existence is therefore vastly higher than the probability of our vast structured reality. According to this logic, you are far more likely to be a momentary brain experiencing a hallucination of a universe than a real person in a real cosmos with a real past. Your memories, your sense of self, the screen you seem to be looking at right now, all of it could be an elaborate illusion fabricated in an instant, destined to dissolve back into chaos a moment later. This is not science fiction. It is a genuine philosophical problem that emerges from our best understanding of statistical physics and cosmology. It forces us to confront a horrifying question. How can we trust that our past is real and that we are not just transient flukes in an endless, mindless void? The fact that we consistently observe a coherent, law-abiding universe that has existed for billions of years is powerful evidence against this bizarre hypothesis. Our reality seems too stable, too interconnected to be a fleeting mirage. Yet the paradox remains, a stark reminder that our very existence pushes against the limits of what probability can comfortably explain. We are left holding onto the order we see, trusting that the cosmos is fundamentally real, even as the numbers whisper a far more lonely and bizarre possibility. This bizarre paradox, with its disembodied brains and fleeting illusions, forces us to seek a more stable foundation for reality. Perhaps the answer lies not within our universe but outside of it. The unsettling precision of nature's constants, the inexplicable flatness, and the matter-antimatter imbalance might all find a single, sweeping explanation in a truly colossal concept, the multiverse. Imagine a boundless cosmic ocean, an infinite froth of bubbles, each one a separate universe with its own unique set of physical laws. In this vast landscape, our universe is just one tiny bubble among an uncountable number. In most of these universes, the cosmic dials are set to random values. Gravity might be too weak to form stars, the nuclear force too strong to allow for complex atoms, or the cosmological constant might be so immense that space tears itself apart in an instant. These are dead universes, stillborn realms where life is an impossibility. But in an infinite sea of possibilities, every combination, no matter how unlikely, must occur somewhere. By pure statistical chance, a few bubbles, a vanishingly small fraction, will have all the dials set just right. In these rare and special universes, matter can coalesce, stars can ignite, and life can eventually emerge. We do not live in a universe that was fine-tuned for us. We live in one of the rare universes that randomly happen to be tunable. Our existence is not a miracle, it is a selection effect. We could not possibly be asking these questions in a universe that could not support us. This is the anthropic principle in its most potent form. It transforms the question from why is our universe so special to how could we be anywhere else. The multiverse idea emerges naturally from some of our most promising theories of fundamental physics, like string theory and the theory of eternal inflation. It suggests that the initial conditions of our Big Bang were not a one-time event, but a local phenomenon within a much grander, perhaps eternal, metacosmos. The razor's edge balance we observe is not a product of design, but a consequence of our limited perspective. We are like a lottery winner marveling at their own luck, unaware of the millions of other tickets that lost. The staggering odds against our existence are no longer puzzling, they are inevitable. For every universe like ours, there are trillions upon trillions of failed experiments. This idea is both humbling and liberating. It removes the need for a cosmic architect, replacing it with the brute force of infinite probability. Yet it also presents a profound challenge. If the multiverse is real, then the ultimate laws of nature are not the specific numbers we measure here, but a much broader landscape of possibilities. Our most cherished constants, like the speed of light or the charge of an electron, are not fundamental truths. They are merely local bylaws, the parochial rules of our own cosmic neighborhood. This pushes science into uncharted territory. How can we test for the existence of other universes, realms forever beyond our observational horizon? Some scientists look for subtle imprints on the cosmic microwave background, potential bruises from collisions with other bubbles in the cosmic foam. Others search for mathematical consistency, hoping the unique structure of our laws points toward a deeper, multiverse-generating theory. The multiverse may be the most elegant solution to the fine-tuning problem, but it also expands the mystery to an almost incomprehensible scale. We are left to wonder if we inhabit a single, unlikely oasis, or just one small planet in an infinite archipelago of realities. Yet for all its grand appeal, the multiverse idea faces fierce criticism from both scientists and philosophers. The most common objection is starkly simple: it is not science. A fundamental tenet of the scientific method is that a theory must be testable and falsifiable. We must be able to imagine an observation that could prove it wrong. But how do we test for the existence of other universes, realms that are by definition permanently beyond our reach? Any evidence we find within our own cosmos will always be consistent with a single universe. The multiverse, its detractors argue, is not a scientific theory at all, but a metaphysical assumption. It risks explaining nothing by proposing everything. If every possible physical law exists somewhere, then our specific laws lose their power to explain why our universe is the way it is. The theory becomes immune to disproof, and in doing so, it steps outside the bounds of empirical science. Another profound problem is that of infinite regress. The multiverse does not truly answer the question of why our universe exists. It simply relocates the mystery. We are left asking, where did the multiverse itself come from? What are the laws that govern this greater metacosmos, this cosmic foam from which our bubble emerged? Those overarching laws would themselves need to be fine-tuned to allow for the perpetual creation of new universes. The same razor's edge precision we sought to explain simply reappears at an even higher level. We have not solved the fine-tuning problem, we have merely pushed it back one step, inviting an endless chain of who created the creator. This feels less like a solution and more like a clever way to delay the ultimate question. There is also a philosophical unease with the multiverse. It attempts to use probability to explain away the staggering unlikelihood of our existence, but this leads to a strange conclusion. If every possible universe exists, then there are not just versions where you are reading this script, but versions where you are a king, a potato, or a being of pure energy. There are universes where the laws of logic are different, where 2 + 2 = 5. In a truly infinite multiverse, everything that can happen does happen an infinite number of times. This vast proliferation of realities can feel like it cheapens our own existence. Is our specific story, with all its unique joys and sorrows, rendered meaningless because an infinite number of other versions are playing out simultaneously? The multiverse offers a cosmic answer, but it may rob our local reality of its singular significance. Ultimately, the multiverse hypothesis stands at a difficult crossroads. It is a breathtakingly elegant idea that emerges from our most advanced mathematics, yet it remains stubbornly out of reach of direct confirmation. It promises to dissolve the miracle of fine-tuning into the mundane statistics of infinite chance, yet it introduces new and perhaps deeper mysteries of its own. Does this mean we should abandon the concept, or does it simply highlight the limitations of our current scientific framework? The search for why the universe should not exist has led us to the very edge of knowledge, where science, philosophy, and the fundamental nature of reality become inextricably intertwined. This line of reasoning brings us directly to the anthropic principle. It is an idea that attempts to anchor our bewildering existence in a simple, self-evident fact. We are here, the universe must be compatible with our existence, otherwise we would not be around to notice it. This seems almost too straightforward, but it comes in two distinct forms, one that is almost trivial and another that is profoundly controversial. The weak anthropic principle is a statement of observational selection bias. It says that the physical constants we measure must be within the narrow range that allows for the emergence of carbon-based life, because that is the only kind of universe we could possibly find ourselves in. Imagine a vast, dark forest filled with pockets of air with different compositions. Most of the air is poisonous, but a few isolated clearings have breathable oxygen. You wake up in one of these clearings. It would be absurd to ask why the air around you is so perfectly tuned for your lungs. You could not have woken up anywhere else. In the same way, we could not have evolved in a universe where gravity was too strong for stars to form, or where atoms could not bind together. Our observation automatically filters for a life-permitting cosmos. This is not an explanation for the constants, but a logical constraint on which ones we are capable of observing. The strong anthropic principle, however, takes a much more audacious leap. It proposes that the universe must have properties that allow life to develop within it at some stage in its history. This statement shifts from a simple observation about our location to a seemingly active principle about the cosmos itself. It suggests that the laws of physics are not just a happy accident we stumbled upon, but that they are in some sense required to produce observers. This is where the principle begins to feel like a tautology, a circular argument that explains nothing. Saying the universe is the way it is because we are here does not tell us why it is that way in the first place. It is like finding a perfectly crafted key and a lock, and concluding the lock must exist because the key fits it so well. The key's existence does not explain the lock's intricate design. The strong version often veers into metaphysical territory, hinting that consciousness itself might be a fundamental feature of the cosmos, a goal toward which the universe is striving. Critics argue this is not science, but a philosophical stopgap that halts further inquiry. If we accept that the universe is fine-tuned for life because we are here to see it, then we have ended the conversation. We have replaced a scientific why with a logical inevitability. Yet, for all its circularity, the anthropic principle forces a crucial perspective shift. It reminds us that our data point of one universe is profoundly biased. We are not random observers of the cosmic lottery, we are the winners. And the very fact that we can debate whether our existence is a tautology or a profound clue might be the most important piece of data we have. Cosmic inflation promised to sweep away our deepest cosmological puzzles. It elegantly solved the horizon problem by suggesting the entire observable universe was once a tiny, interconnected speck that inflated to cosmic size. It also addressed the flatness problem, explaining how the relentless stretching of space drove the universe toward that perfect geometric balance we observe today. For a time, it seemed we had found the master key, a single mechanism that could explain the universe's impossible smoothness and shape. Yet this brilliant solution came with a hidden and profound cost. The very engine of inflation appears to demand its own form of fine-tuning, creating a new layer of mystery beneath the one it resolved. For inflation to work as described, the field that drove it, often called the inflaton, had to possess incredibly specific properties. It needed to switch on with just the right amount of energy to initiate a period of hyper-accelerated expansion. More critically, it had to shut off at exactly the right moment. If the inflation field had decayed a fraction of a second too early, the universe would not have grown large enough to become flat and smooth. The expansion would have fizzled, leaving behind a small, lumpy cosmos incapable of supporting life. But if the field had persisted for even a sliver of a second too long, space would have been stretched into a near-total void. Matter would be so hopelessly diluted that no galaxies could ever form. The graceful exit from inflation required a precision that rivals the fine-tuning of the cosmological constant itself. We have replaced one set of perfect initial conditions with another, simply pushing the mystery of why back to an even earlier moment. This leads to the multiverse scenario, a dramatic and unsettling consequence of the theory. Most models of eternal inflation suggest that once started, the process never truly stops. While inflation ends in our local patch of reality, creating our Big Bang and the universe we know, the overarching inflationary field continues to expand elsewhere. It spawns an endless cascade of bubble universes, each with its own random physical properties. Our finely tuned cosmos, in this view, is not the product of a one-time miracle, but a single lucky draw from an infinite cosmic lottery. While this seems to explain our good fortune, it also implies that the vast majority of these bubble universes are barren, stillborn realms where the laws of physics are hostile to complexity or life. The theory that sought to explain our unique order ultimately predicts that we are profoundly ordinary, just one of countless islands in a chaotic and infinite meta-ocean. So we are left at a crossroads. Inflation brilliantly patches the holes in the standard Big Bang model, but at the price of introducing its own razor's edge requirements. We are faced with a difficult choice. Do we accept that the universe began with an inexplicably perfect state that allowed for inflation to occur? Or do we embrace an infinite multiverse where our existence is a statistical inevitability, yet forever beyond the reach of scientific confirmation? Both answers feel deeply unsatisfying. One requires a miracle at the beginning, while the other dissolves the concrete reality of our universe into a phantom in an endless crowd. The quest to understand why we are here has led us to a theory that saves the phenomena but challenges the very meaning of a final explanation. Perhaps this is the true boundary of our knowledge, a horizon beyond which our current tools of science and reason cannot yet see. The universe's fragility extends to the very forces that govern its smallest pieces. We are held together by a delicate balance of fundamental interactions, a balance that, on closer inspection, seems mathematically absurd. This is the hierarchy problem, a profound mystery in particle physics that asks why gravity is so unbelievably weak compared to the other forces. The difference in strength is not just large, it is incomprehensible. The electromagnetic force that binds atoms is 10 to the power of 36 times stronger than gravity. That is a 1 followed by 36 zeros. To grasp that scale, imagine the entire planet Earth on one side of a cosmic tug-of-war and a single, solitary bacterium on the other. That bacterium represents the strength of gravity. This immense gap is puzzling enough, but it creates a catastrophic problem for the very particle that gives mass to everything, the Higgs boson. According to quantum field theory, the mass of the Higgs boson should be constantly pushed upward by its interactions with every other particle in existence. Virtual particles flickering in and out of the vacuum should be screaming their influence into the Higgs field. These quantum corrections should drive the mass of the Higgs to the highest possible energy scale in nature, the Planck scale. This is the energy at which gravity becomes as strong as the other forces, a realm where the very concepts of space and time break down. If this happened, the Higgs mass would be a staggering 10 to the power of 19 times heavier than what we actually observe. The consequences of such a heavy Higgs boson would be immediate and absolute. The delicate balance of the forces that form atoms would be completely shattered. Electrons would not be able to stably orbit atomic nuclei. The very structure of matter would be impossible. No atoms could form, which means no molecules, no chemistry, no stars, no planets, and no life. The universe would be a sea of unstable, fleeting particles incapable of building anything. Yet we exist. We measure the Higgs boson, and its mass is not at the Planck scale. It is light, almost impossibly so. For the Higgs to remain this light, the violent quantum screams from the virtual particles must be almost perfectly cancelled out. The positive contributions to its mass must be matched with exquisite precision by negative contributions. This cancellation is not just a little fine-tuning. It requires a precision of 1 part in 10 to the power of 34. It is as if two colossal, opposing forces were locked in a battle, each with the power to shake the foundations of reality, and they somehow balance so perfectly that the net result is the faintest, most gentle whisper. Physicists find this level of accidental balance deeply unsatisfying. It feels like a cosmic cheat, a mathematical miracle with no underlying reason. This is not a feature of our theories, it is a glaring bug. It suggests that we are missing a fundamental piece of the puzzle, a new symmetry or a new particle that naturally enforces this delicate balance and protects the Higgs mass from soaring to its seemingly natural, catastrophic value. The search for this missing piece is one of the most urgent quests in modern physics. It is a quest that forces us to look beyond the world we see, toward a deeper, more balanced reality hiding just beyond our current sight. This relentless march toward disorder is written into the fundamental laws of physics. The second law of thermodynamics states that entropy, a measure of chaos or randomness, always increases in an isolated system. The universe as a whole is the ultimate isolated system, which means its total entropy is always rising. This is the arrow of time, the reason we remember the past and not the future, why a shattered glass does not spontaneously reassemble itself. The natural, most probable state for any system is one of maximum entropy, a featureless soup where everything is the same temperature and energy is evenly distributed. This is called thermal equilibrium, a cosmic lukewarm bath where nothing interesting can ever happen. And this is where the mystery of our existence deepens to a startling degree. The early universe, as revealed by the cosmic microwave background, was in a state of incredibly low entropy. It was not a random, chaotic mess. It was exquisitely smooth and ordered, like a perfectly wound spring. Think of a brand new deck of playing cards, fresh from the box, with all the suits in perfect sequence. That is a state of low entropy. Now shuffle that deck thoroughly. The cards become a random jumble, a state of high entropy. The universe began in that pristine, ordered state, and it has been shuffling itself ever since. The profound question is, why did it start so perfectly ordered? Why was the deck fresh out of the box? A state of high entropy, a completely shuffled cosmic deck, is astronomically more probable. For the universe to give rise to galaxies, stars, and life, it needed that initial store of order to burn, just as an engine needs concentrated fuel to run. If the universe had begun in a high entropy state of thermal equilibrium, it would have been stillborn. There would have been no temperature differences to drive the formation of structures, no energy gradients to power stars, no free energy to fuel the complex chemistry of life. It would have been a vast, quiet, and eternal fog of uniform sameness. The probability of our universe starting with such a low entropy configuration is so vanishingly small that it is like tossing a coin and having it land on its edge every single time for billions of tosses in a row. This is the real puzzle of the arrow of time. The laws of physics do not care about the direction of time. They work just as well running forward or backward. So why do we only experience time moving in the direction of increasing entropy? The answer seems to be that we are living in the aftermath of a supremely unlikely starting point. Our entire history, from the first star to the thought in your mind, is the unfolding of that initial cosmic windfall, the slow and majestic cascade of order into chaos. We are not just improbable in our physical constants, we are improbable in our very history. The universe had to be born with a past that was inexplicably more organized than its present. This low entropy beginning is the ultimate free lunch that made everything else possible, and we still have no fundamental explanation for why it was served. The profound improbability of our universe extends even to the simple act of observation. At the tiniest scales, particles exist in a ghostly state of pure potential called a wave function. An electron is not in one place or another. It is a cloud of probability, existing everywhere it possibly could be at once. This is the bizarre and beautiful world of quantum mechanics. Yet when we measure that electron, this cloud of possibilities collapses. We find the particle in one definite location, as if our very act of looking forced it to make a choice. This is the quantum measurement problem. Why does the act of observation shatter this world of potential into a single, concrete reality? The mathematics of the wave function offers no answer. It simply describes a particle as a shimmer of probabilities until the moment it is measured, when it abruptly snaps into a single point. This transition from the quantum blur to our sharp, classical world has no clear trigger. It is a gaping hole in our understanding of reality. One interpretation, the many worlds hypothesis, proposes a staggering solution. It suggests the wave function never actually collapses. Instead, at the moment of measurement, reality splits. Every single possible outcome of a quantum event actually occurs, but each one plays out in a newly branched parallel universe. In one universe, you find the electron here. In another, an identical version of you finds it there. This means that for every quantum decision, every random flicker of a particle, the cosmos is constantly fracturing into an ever-growing tree of alternate histories. In this view, our specific, seemingly stable universe is not the main event. It is just one thread in an infinite tapestry of realities. The reason we experience a single, consistent timeline is not because the other possibilities vanish. It is simply because our conscious awareness is locked onto one single branch, unable to perceive the others. This makes our orderly, classical existence a profound statistical anomaly. An infinite number of chaotic, wildly different universes are being created every instant, but we only inhabit one of the relatively stable ones that can support conscious observers. We are not special, we are just isolated. The many worlds idea tries to restore the purity of the quantum equations by sacrificing the uniqueness of our reality. It dissolves the mystery of the collapse by suggesting that everything that can happen does happen somewhere. Yet this comes at a great cost. It asks us to believe in an unimaginable plurality of worlds, all equally real, branching from every quantum event since the beginning of time. Our journey to understand why the universe should not exist has led us to a place where it may, in fact, exist in every possible way. This final layer of the mystery may be the deepest of all. We have journeyed through the cosmos, from the impossibly precise constants to the quantum foam, all to answer why we are here, but this leads to an unavoidable question. Why is there someone here to ask the question in the first place? You are not just a collection of atoms, you are an experience. You feel the warmth of sunlight, the ache of sadness, the vivid red of a sunset. This inner, subjective world is what philosophers call consciousness, and its existence is the most intimate fact of your life, yet it is completely absent from our physical descriptions of the universe. We can map a brain in exquisite detail, we can see neurons firing and chemicals flowing, but we cannot find the feeling of pain in a PET scan. We cannot locate the color blue inside a nerve cell. This is the hard problem of consciousness. How does the objective, mechanical churning of matter inside a skull give rise to the rich, private movie of your inner life? It seems to be a different kind of reality altogether. This problem forces us to consider a radical possibility. What if consciousness is not a late arriving product of the universe, but a fundamental feature of it, as basic as space and time? Perhaps the universe is not a mindless machine that accidentally generated awareness. Perhaps it is a structure that, from its very beginning, had the potential for experience woven into its fabric. In this view, the fine-tuning we have explored takes on a new and startling significance. The constants are not just set for life, they are set for conscious life. The cosmos evolved in this specific way because this is one of the few pathways that allows the universe to wake up and observe itself. The laws of physics appear fine-tuned for our existence because they are the prerequisite for any existence to be known. Without a conscious observer, is a tree real if it falls in a forest with no one to hear it? The question is not just philosophical. In quantum mechanics, the role of the observer is deeply puzzling, as the act of measurement seems to crystallize reality from a haze of possibilities. This has led some scientists and thinkers to propose that consciousness is not a passive bystander, but an active participant in shaping the world. The universe exists in a definite state because it is being observed. This idea, while controversial, offers a profound twist on the anthropic principle. It suggests we are not just lucky to be in a universe that allows us. Our presence as observers is the very reason this particular universe has solidified into being. We are not just reading the cosmic story, we are writing it with every glance. This perspective turns the mystery inside out. The universe exists because it is perceived. The intricate, improbable fine-tuning that allows for galaxies and carbon and brains is not a random fluke, but the necessary scaffolding for a cosmos that can become aware of itself. You are not a stranger in a strange land. You are the universe feeling its own existence for the very first time. This strange entanglement of mind and cosmos pushes us toward the final frontier of explanation. What if the universe is not just described by mathematics, but actually is mathematics? This is the core of the mathematical universe hypothesis proposed by physicist Max Tegmark. It is a proposition so simple and radical it challenges everything. Our physical reality, with all its galaxies, forces, and conscious beings, might not be a machine running on mathematical rules. It might be those rules. In this view, the universe is not just computable, it is a specific, gigantic mathematical structure. The objects of this structure are not made of atoms, but of abstract mathematical relationships. You, the screen you are looking at, the space between us, are all just complex patterns in this structure. So what does it mean for a mathematical structure to exist? In the abstract world of math, a circle exists as a perfect idea the moment you define it as the set of all points equidistant from a center. It does not need to be drawn on a page to be true. Its existence is logical and necessary. In the same way, if a particular mathematical structure is self-consistent, if its internal rules do not lead to contradictions, then it exists in a timeless, placeless realm of mathematical truth. The mathematical universe hypothesis takes this one step further. It suggests that every self-consistent mathematical structure has its own physical reality. Our cosmos is not special. It is simply one of many mathematical structures that, by virtue of being logically consistent, instantiate a universe. This idea offers a breathtakingly simple answer to the question of why there is something rather than nothing. Nothingness, true nothingness, may be impossible because mathematical truths are necessary. They cannot not exist. A world where 2 plus 2 does not equal 4 is not a different kind of something. It is a logical absurdity. So existence, in this view, is not a contingent, shaky fact. It is a logical inevitability. The real mystery is not why there is a universe, but why we find ourselves within this particular mathematical structure, with its specific laws and constants, and not another. The fine-tuning we have explored might simply be a selection effect. Our structure is one of the rare ones that contains self-aware substructures, like us, capable of wondering about our own origins. We are not a cosmic accident, but a necessary pattern within an eternal mathematical tapestry. This hypothesis dissolves the boundary between the physical and the abstract, suggesting that the ultimate reality is not made of stuff but of information. The universe just is. It could not have been otherwise. This strange mathematical view of reality opens the door to an even more startling possibility. If our universe is, at its core, a set of information and rules, then what is to stop a vastly advanced civilization from running that program? This is the simulation argument, a modern hypothesis suggesting that our entire cosmos might be an artificial construct, a digital reality created by beings whose technology is indistinguishable from magic. The fine-tuning we have wrestled with, the constant set with such impossible precision, could simply be the default settings of the simulation. The laws of physics are not fundamental truths of nature, they are the software parameters chosen by the programmers. Think of a video game. The world inside that game operates under a strict set of rules. Gravity might be set to a certain strength, the speed of light might be capped at a certain value, and the behavior of materials is defined by the game's code. To the characters within the game, these rules are the unchanging laws of their universe. They have no way of knowing they are living in a simulated reality. From our perspective, we can easily adjust the game's code, changing the strength of gravity or the properties of matter with a few keystrokes. In the same way, our own physical constants might seem arbitrary and finely tuned to us, but they could be easily adjustable variables from the perspective of the simulators. This idea offers a chillingly elegant solution to the cosmological constant problem. Why is the energy of empty space so close to zero when our theories predict a cataclysmic value? Perhaps because the programmers set it that way to ensure the simulation remains stable and does not instantly tear itself apart. The matter-antimatter asymmetry, the inexplicable flatness, the low entropy beginning, all of these could be initial conditions loaded into the simulation to produce an interesting and complex output, a universe rich with galaxies and life. The argument gains weight when we consider our own technological trajectory. We are already creating increasingly sophisticated virtual worlds. Our video games are evolving from simple, blocky environments into vast, open worlds with their own physics and ecosystems. If our civilization continues to advance for thousands or millions of years, it is not far-fetched to imagine that we could one day run simulations of entire universes, complete with sentient beings who believe their world is real. Now, if such a future is possible, then we are faced with a simple statistical truth. The number of simulated universes created by advanced civilizations would eventually vastly outnumber the one original, base reality. Therefore, if you randomly pick a conscious being from the multiverse of all possible experiences, the odds are overwhelmingly high that you would find yourself in a simulation, not in the original physical world. This logic suggests that it is more probable than not that we are living in an artificial construct, but how could we ever know? Some scientists speculate that the programmers might have cut corners, leaving subtle artifacts in the fabric of our reality. Just as a video game might have a lower resolution in the distance to save processing power, our universe might exhibit tiny computational flaws at the very smallest scales, in the patterns of high-energy cosmic rays or in the behavior of fundamental particles. The search for these glitches is a serious, if fringe, scientific endeavor. The simulation hypothesis transforms the deepest questions of existence. It reframes the anthropic principle. We exist not because the universe is fine-tuned for life, but because a universe fine-tuned for life is more likely to be simulated. It is a selection effect on a cosmic scale. The profound mystery of why there is something rather than nothing is replaced by a different, equally dizzying question. Who or what is running the code, and what was their reason for booting up our particular instance of reality? Our scientific journey through cosmic improbability leads us to a realm of thought as vast as the universe itself. For millennia, long before telescopes or particle colliders, humanity grappled with the same fundamental mystery using a different toolkit, that of faith and reason. Religious and philosophical traditions across the globe have constructed their own profound narratives to explain why there is a world at all, offering answers that sometimes clash with and sometimes curiously echo our modern scientific story. In the Abrahamic traditions of Judaism, Christianity, and Islam, the answer is creation from nothing, or creatio ex nihilo. This is the powerful idea that a transcendent, timeless God spoke the cosmos into being, not from pre-existing materials, but from absolute nothingness. This divine act was one of pure will, establishing the laws of nature and the fabric of space-time in a single, foundational moment. The universe is therefore a deliberate artifact, a thought made real, with its fine-tuning reflecting the mind of a cosmic architect. This stands in stark contrast to the scientific picture of a spontaneous quantum fluctuation or a multiverse of random chance. Here, the constants are not lucky, they are chosen. The question of why we exist finds its answer in purpose and intention. Yet this solution raises its own deep inquiries. What existed before God, and what was the nature of the nothing from which everything was summoned? These are mysteries that faith places beyond the reach of human reason. Meanwhile, Eastern philosophies often present a radically different vision. In Hindu cosmology, for instance, the universe is not a one-time event. It is an endless, rhythmic dance of creation, preservation, and dissolution. A single breath of the god Brahma lasts for billions of our years, and with each exhalation, a universe blossoms into being, only to be drawn back into a divine unity with the next inhalation. This is a cyclic model without a true beginning or end, where our current cosmos is just one note in an infinite cosmic symphony. Buddhism, with its emphasis on dependent origination, suggests that asking about the ultimate origin of the universe is a misunderstanding. Existence is a web of interconnected causes and conditions, a perpetual flow without a first cause. The universe simply is, and our task is to understand our place within its interdependent nature, not to seek a primal starting pistol. Ancient Greek philosophers approached the puzzle through pure logic. Parmenides argued that nothing cannot exist, and therefore something must have always existed. The universe was eternal and unchanging. Others, like Aristotle, postulated an uncaused cause, a prime mover that set the cosmos in motion without itself being moved. These philosophical systems sought to ground existence in necessary first principles, using the power of the human mind to deduce why reality could not be otherwise. The common thread weaving through these diverse perspectives is the human need to find meaning. The scientific narrative, for all its power, tells us we are a statistical fluke in an indifferent multiverse. The religious narrative offers purpose and design at the cost of placing the ultimate cause beyond scientific inquiry. The philosophical narrative seeks a logical necessity that often feels abstract and distant from our lived experience. Each framework provides a different kind of comfort and a different set of challenges. They are not necessarily in conflict, but are different languages attempting to describe the same indescribable truth. One seeks the how, the other the why, and both are left staring into the same profound mystery, humbled by the simple, staggering fact that anything is here at all. This cosmic architecture, from the largest galaxy clusters to the smallest atoms, is built upon a foundation we cannot see. Over 95% of the universe is made of two invisible and mysterious components, dark matter and dark energy. We know they exist only by their profound gravitational effects on the ordinary matter that forms our world. Their values are not just arbitrary numbers, they are dials that were set with a precision that allowed our universe to become structured and long-lived. Dark matter acts as the cosmic scaffolding. In the early universe, ordinary matter, the stuff that makes up stars and planets, was too hot and energetic to clump together under its own gravity. It was dark matter, cold and sluggish, that first collapsed into vast, invisible webs. Its gravitational pull created the deep wells that then drew in the normal matter, seeding the formation of the very first galaxies. Without dark matter, there would be no anchor points for structure. The universe would be a thin, uniform soup with no galaxies, no stars, and no planets. The amount of dark matter had to be just right. If there were too much, its intense gravity would have forced galaxies to form too early and too close together, leading to violent collisions and a chaotic cosmos. If there were too little, the gravitational wells would have been too shallow, and matter would never have gathered into the majestic spirals and ellipticals we see today. Dark energy, on the other hand, plays the opposite role. It is the mysterious force driving the accelerating expansion of the universe. For billions of years, gravity was the dominant force, slowing down the initial expansion of the Big Bang. But then, around 5 billion years ago, dark energy took over. Its gentle, repulsive pressure began pushing the cosmos apart at an ever-increasing rate. The value of dark energy, what we observe as the cosmological constant, is so tiny it seems absurd. Yet if it were significantly larger, even by a minuscule amount, it would have dominated the universe from the very beginning. That accelerated expansion would have ripped apart every proto-galaxy before it could even form. The cosmos would have been blown into a meaningless, ever-thinning mist. The timing of its dominance is also a miracle. Dark energy waited until the universe was mature, after galaxies had formed and stars had forged the heavy elements necessary for life before making its presence known. If it had surged earlier, structure would have been impossible. If it had been weaker, gravity might have eventually reversed the expansion, crushing the entire universe in a catastrophic big crunch. The balance between dark matter's pull and dark energy's push is what has given our cosmos both its rich structure and its long-term stability. Yet for all their cosmic importance, we have no idea what they actually are. Dark matter could be a sea of undiscovered particles, a trillion of them passing through your body every second without a trace. Dark energy could be a property of empty space itself, or it could point toward a complete revision of gravity. They are the two greatest puzzles in modern cosmology, and they are also the two most critical ingredients for our existence. Their precise values feel less like a random draw and more like a carefully set stage, allowing the cosmic play to unfold exactly as it has. But this grand cosmic architecture, built on dark scaffolding and pushed by dark energy, rests on a foundation that is fundamentally cracked. Our two most powerful descriptions of reality, general relativity and quantum mechanics, are at war with each other. One paints the cosmos on a vast canvas of curved space-time, while the other sketches the frantic dance of particles in a fuzzy, probabilistic world. Each theory is spectacularly successful in its own domain, but they speak different languages and obey different rules. When their territories overlap in places of extreme gravity and tiny size, their equations break down into meaningless infinities. This is the quantum gravity conundrum, and it means our entire picture of the universe is incomplete. We are trying to understand a masterpiece while missing the theory of paint. The most critical place where this conflict becomes absolute is at the Planck scale. This is the universe's ultimate resolution limit, a distance so small that the very concepts of space and time lose all meaning. At this scale, the smooth, geometric fabric of general relativity should be replaced by a seething, chaotic foam, a place where tiny wormholes blink in and out of existence, and gravity is just another quantum force. This is the realm where the Big Bang began, where black holes hide their singularities, and where the true nature of the cosmos might be written. Yet here, at the very threshold of ultimate understanding, our physics simply stops working. Our equations spit out nonsense. This is more than a technical problem, it is a conceptual crisis. Our inability to peer into this domain means we might be completely misreading the cosmic fine-tuning. The constants that seem so impossibly precise to us, the gravitational constant, the strength of the nuclear forces, the value of the cosmological constant, might not be fundamental at all. They could be emergent properties, like the temperature of a gas emerging from the collective motion of trillions of molecules. From our limited perspective outside the quantum gravity realm, these numbers appear fixed and fine-tuned. But what if, deep within the Planck foam, they are the only possible outcomes? A theory of quantum gravity could reveal that these values are not freely adjustable dials, but are locked into place by a deeper, more elegant mathematical consistency. The universe may not be fine-tuned, it may be inevitable. The apparent miracle of our existence could be a simple consequence of laws we have not yet discovered. The cosmological constant problem, for instance, where the energy of empty space is 120 orders of magnitude smaller than predicted, might vanish entirely. A complete theory could naturally cancel out this vacuum energy, leaving behind the faint whisper we observe, the initial low entropy state of the universe. That perfectly ordered beginning might be the only way a cosmos can be born from the quantum gravitational vacuum. We are like detectives at a crime scene, looking at the aftermath and marveling at the unlikely placement of every piece of dust, unaware that the entire scene was orchestrated by a hidden logic. Our current physics only describes the dust. The search for this final theory is the greatest quest in fundamental physics. Efforts like string theory propose that all particles are minuscule, vibrating strings, and that the constants of nature are determined by the way the universe's extra, hidden dimensions are curled up. Loop quantum gravity suggests that space itself is woven from a network of discrete, finite loops, eliminating the infinities that plague other models. Each approach is a breathtaking leap of imagination, yet each remains, for now, beyond the reach of experimental proof. They are maps of a territory we cannot yet visit. Until we can build experiments that probe the Planck scale or observe the echo of the Big Bang with enough precision, the quantum gravity conundrum remains the final veil over the cosmos's deepest secrets. It stands as a humbling reminder that our entire reality, from the largest galaxy to the smallest thought, might be built upon rules we have only begun to glimpse. This profound cosmic solitude might be the ultimate consequence of our improbable existence. The universe is not just fine-tuned for life, but seemingly for our specific kind of life, and that leads to one of the most haunting questions in science, the Fermi paradox. If the cosmos is so vast and ancient, with hundreds of billions of galaxies, each containing billions of stars, then where is everybody? The sheer number of potential worlds should mean the galaxy is teeming with civilizations, their signals crisscrossing the void. Yet when we listen, we are met with an eerie and profound silence. This silence becomes deafening when viewed through the lens of cosmic fine-tuning. The journey from the Big Bang to a talking, technological species like us required not just one miracle, but a long and unbroken chain of them. Every step, from the exact strength of gravity that allowed galaxies to form, to the precise nuclear forces that forged carbon in stellar furnaces, to the fragile balance that gave our planet a stable climate for billions of years, was a razor's edge victory. Now consider that every one of these fine-tuned parameters, from the cosmological constant to the matter-antimatter asymmetry, had to be just right not just once, but in every single star system where intelligent life might arise. The universe itself had to be habitable, and then local planets within it had to be habitable too. This stacks improbability upon improbability. Perhaps the reason we do not see other civilizations is because the filters are too strong. The Great Filter hypothesis suggests that at some point between non-life and a spacefaring civilization, there is a barrier that is almost impossible to cross. We used to wonder if the filter was behind us, something like the emergence of life itself or the evolution of multicellular organisms. But if the universe is so finely tuned that life-bearing realities are themselves one in a trillion, then the filter is not behind us, it is woven into the very fabric of the cosmos. The universe is mostly dead by default. The silence of the heavens then becomes a chilling confirmation. We are not just alone in our galaxy, we might be alone in the entire observable universe, a single, fleeting thought in an otherwise mindless and empty cosmos. Our existence is not just a statistical fluke, it is a statistical miracle of such magnitude that we may be the only ones who ever achieved it. The very laws of physics that allowed us to be might also be the laws that condemn us to eternal solitude. This silent, empty cosmos hints at a reality far stranger than we ever imagined. Perhaps the very stage upon which the universe plays out the familiar dimensions of space and time is not the final layer of the mystery. What if the empty void and the relentless tick of the clock are not fundamental at all, but are themselves illusions that emerge from a deeper, more basic level of reality? This radical idea is gaining traction at the frontiers of theoretical physics. It suggests that the three dimensions of space and one of time we experience are like the smooth surface of a lake. From a distance, it appears continuous and solid, but up close, we see it is made of countless, frenetic water molecules. In the same way, our space-time may be a collective phenomenon, emerging from a vast network of unimaginably tiny building blocks. These fundamental constituents would not exist in space and time. They would create the concepts of space and time through their interactions and connections. Think of a three-dimensional movie. The image has depth and volume, but that reality is projected from a flat, two-dimensional screen. Our universe might be a similar kind of projection, a hologram arising from a two-dimensional surface at its boundary. The information needed to describe every star, planet, and person within the cosmos could be encoded on this distant, lower-dimensional shell. This is the holographic principle, a stunning consequence of our attempts to reconcile gravity with quantum mechanics. It implies that the world we perceive is a kind of illusion, a useful and consistent one, but an illusion nonetheless. The smooth geometry of general relativity would then be a large-scale approximation, much like the smoothness of a piece of fabric emerges from the weaving of individual threads. At the most fundamental level, reality might be digital, composed of discrete bits of information. The flow of time itself could be an emergent property. We feel time passing in one direction, but at the quantum level, the equations are often timeless. The sensation of a past, present, and future could arise from the increasing complexity of correlations between these fundamental building blocks, a phenomenon known as quantum entanglement. When two particles become entangled, their fates are linked, no matter how far apart they travel. A change to one instantly affects the other. Now, imagine the entire cosmos as an immeasurably complex web of such quantum links. The orderly flow of time we experience could be the result of this cosmic network becoming more and more entangled. Our forward-moving timeline is not a fundamental river, but the unfolding of cosmic connections. This perspective offers a potential explanation for the ultimate fine-tuning question, why our particular spacetime configuration exists. If spacetime is emergent, then the specific laws of physics we observe, the four dimensions, the precise constants, are not arbitrary dials set at the beginning. They are the only possible stable configuration that could emerge from the underlying quantum chaos. Countless other mathematical structures might be possible in the abstract, but they would be unstable, instantly collapsing or failing to cohere into a continuous reality. Our universe is not one choice among an infinite menu. It is the one stable structure that can hold itself together long enough for galaxies and minds to form. The apparent fine-tuning is not a selection from a multiverse, but a natural consequence of mathematical stability. The universe had to be this way because any other way would not be a universe at all, just a fleeting, inconsistent flicker in the void. We are not living in a finely tuned cosmos, but in the only cosmos that could last. The evidence for our impossible existence is overwhelming. From the razor's edge balance of gravity to the ghostly dominance of dark matter, every law of physics seems to conspire to allow us to be here. We are living proof of a cosmic lottery won against odds so vast they defy comprehension. This leaves us standing at a precipice, staring into the heart of a mystery that science alone may never fully resolve. Does this staggering improbability point toward a deeper, more elegant set of laws we have yet to discover, laws that make our universe the only logical outcome? Or is the very act of our observation, our conscious presence here and now, the final piece of the puzzle? Perhaps the universe exists for no other reason than that we are here to witness it. The question of why there is something rather than nothing may ultimately find its answer not in a distant galaxy or a complex equation, but in the simple, profound fact of your own awareness. You are the universe asking itself why it is here.